If you look closely at the spacecraft that have left Earth over the past half-century, you will see familiar shapes and designs recurring over and over again. Generally, you will see a rocket, the shroud, and finally the blunt-body aeroshell that brings a payload through the atmosphere. The reason the shape of the aeroshell has changed little over the years can be summed up in one word: physics. When a spacecraft enters the atmosphere of a planetary body, physical forces like drag, pressure, and heating affect the craft. Because the basic blunt body shape works so well to combat the physics of entry, descent, and landing, it has remained the gold standard for decades. But in order to fit into the rocket shroud, aeroshells have to be relatively small. Even the largest aeroshell ever designed specifically for the Curiosity rover is too small to accomplish many of the goals researchers want to achieve on Mars. Worse yet, it's as large as we can build and still fit into existing rocket shrouds. Unless something drastically changes, we are relegated to sending relatively small rovers to very specific spots on Mars. But a small team at NASA has developed an idea that could be the game changer we needed to begin fitting larger aeroshells into smaller rocket shrouds. Called HIAD, or Hypersonic Inflatable Aerodynamic Decelerator, this idea has the potential to revolutionize entry, descent, and landing on any planetary bodies with an atmosphere, including back here on Earth. On this episode of NASA X, we will follow the HIAD team as they begin real-world testing of this concept with IRVI-3, or the Inflatable Re-Entry Vehicle Experiment. With a short timeline and a small budget, the team worked through numerous challenges to find out if this type of device has what it takes to land future manned and unmanned missions on the Red Planet and beyond. Control room scenes like this one are a common sight for those of us who have followed past NASA missions. But unlike many of the launches of the past, this one is very different. The cargo on board this rocket has the potential to change the way we land on other planets in the years to come. Today's launch will highlight IRVI-3, or the Inflatable Re-Entry Vehicle Experiment. After years of ground testing, development of new materials, and many sleepless nights, NASA researchers will soon know if this new idea will be a viable way to get huge payloads onto other planets. The reason the IRVI-3 test is so significant is because getting payloads to a planet like Mars is very difficult. Whenever we travel to a planet that has an atmosphere, we try to make use of that atmosphere to help us slow down. One way to accomplish this is by using an aeroshell. The unique blunt body shape of the aeroshell is designed to create enough drag on the vehicle to help slow it down, while also serving as a type of cocoon to protect the payload from the heat and pressure. With enough atmosphere, the aeroshell and parachutes can slow the vehicle from hypersonic speeds down to landing speeds. One problem we face on Mars is that the instruments engineers pack inside the rocket shroud are generally very heavy. All this mass behind a small aeroshell, combined with a thin atmosphere, makes slowing down very difficult. Once the aeroshells hit the atmosphere, drag forces help slow the vehicle down. Eventually, the craft slows down to the point where the supersonic parachutes deploy, slowing it even further. To use this technique, the vehicle needs to spend as much time as possible slowing in the atmosphere.
Well, it's a funny thing about Mars, but if you take the average of the planet, the average height of everything in the planet, it turns out that most of the north is 2 kilometers below that, and most of the south is 2 kilometers above that. And it's just, we always land in the north because there's a lot more atmosphere. If we land in the south, it's like 4 kilometers less of air to come to a stop. In fact, at the altitude of the mountains in the south, the Mars Science Laboratory was still supersonic as it was descending into the crater that it was reaching in the north.
This is an obvious problem for researchers because a big part of the planet is inaccessible to them, even with these small rovers. The problem is magnified even more when you consider what it would take to land human missions with all their heavy equipment. The Curiosity rover weighed about 1 metric ton, while the current architecture for human missions state that we would have to land about 40 metric tons to get on the surface. This is where the concept for a HIAD comes in. It can be folded to fit nicely into the rocket shroud, but when we need to deploy it, it could inflate to a size that would act like a giant air brake in the higher altitudes of the atmosphere that see less heating. With this in our arsenal, we would be able to land virtually anywhere on the planet, including the higher elevations of the southern hemisphere. This idea would work for robotic missions, but could also be the game changer we've been looking for to land humans on Mars as well. But until recently, this idea was still far from our grasps. Since the earliest days of NASA, researchers have been interested in inflatable vehicles. In fact, one of the first missions NASA conducted was called Project Echo. This mission utilized 2 large metallized balloon satellites, which were placed in a low Earth orbit. But Echo 1 and 2 were designed to stay in space and not be subjected to re-entry pressures. So after a number of years in space, both balloons finally came back into the atmosphere, burning up on re-entry. The next big push for the inflatable ideas came up again as NASA researchers began considering landing the Viking landers on Mars in 1976. Early testing was promising, but these designs were also not meant to take the stress of entry. Rather, they would deploy after the worst of entry had already taken place. After lengthy study, researchers decided to use supersonic parachutes instead of inflatables, which meant that these unique designs were once again sidelined. One clear result of the testing during that time showed that the materials of the day lagged behind what would be necessary to handle the stresses of entry, descent, and landing. As the mid-2000s rolled along, NASA researchers believed that materials had advanced to the point where they were now both strong and heat-resistant enough to be able to take the stresses related to EDL. One of the first at NASA to begin testing this hypothesis was NASA Langley's Dr. Neil Cheatwood. Along with a small group of engineers, Dr. Cheatwood began thinking about how current materials could be used to create large aeroshells. Their elegant and seemingly simple idea was to build large inflatable aeroshells to get really heavy payloads down to areas that would have previously been impossible. In theory, this seemed like it would work, but a huge hurdle faced by the team was the tightening NASA budget. With a project budget that wouldn't be enough to even buy an economy car, the team began testing. The initial study proved that the idea would work, but the team was a long way from a test flight. They needed to find more funding. With the search for funding in full swing, the team began calling colleagues and friends within NASA, looking for even small amounts of money to help fund the IRVI concept.
I was able, over the next few years, to still find chunks of money here and there. And I used to drive my project manager crazy. I would show up with a new number. I'd say, here's another JO, and he's like, well, how much is on this? I'm like, $762. And that's actually a number. That's actually true. That's the smallest one I gave him. But then it got a little easier to get 50,000 here or 100,000 here, and it started kind of coming together.
Of course, one of the biggest expenditures that the team faced would be acquiring an actual rocket to launch the experiment. Cheatwood found a solution for this after visiting NASA Wallops rocket range.
That first IRVI that we attempted was actually on the smallest rocket we could get. And we ended up there because I had this little bit of money, and I was going to go up to Delaware and sell a contractor on the idea of building us an article. And on the way, I stopped at Wallops flight facility, and they're like, well, we have 1 or 2 tech demo flights a year. They're like, suppose we just let you have one of those missions. I'm like, okay.
With a rocket in hand and a little more funding, the first IRVI test was finally a go to proceed. The team worked tirelessly for more than a year to prepare the first test, and as the rocket fired, hopes were high. But shortly after the rocket left the ground, a malfunction occurred, which did not allow IRVI to deploy.
Unfortunately, that first flight, we had an anomaly with the launch vehicle. So we launched it, but we never came out of it. But at the time, I was serving as the hypersonics project scientist, and the principal investigator for that project said, you know, I believe in your concept, let's refly. And that was huge, because whereas I had been, you know, for the previous 4 or 5 years cobbling together any money I could get, here we basically had the design finished, we thought it was going to work, and we had somebody that's willing to just say, all right, you think it's going to cost $5 million? Here's $5 million, let's do it.
The team quickly began working on the next IRVI test, which was called IRVI 2. They now had enough funding to move forward, and in short order they developed new flight hardware. If successful, the IRVI 2 test would help provide a baseline for future testing. On August 17, 2009, IRVI 2 launched from the Wallops Flight Facility. After the failure of the last test, tensions were high for this flight. The data began streaming back. IRVI 2 had deployed and was feeding valuable information back to the team.
Immediately after IRVI 2 launched, then the hypersonics project said, let's do an IRVI 3. And this time, let's go to the biggest rocket they've got in their standard arsenal. Let's see what kind of heating we can get out of it. And my objective was really to go order of magnitude higher in heating. So we didn't increase the size, because remember, if you increase your size, you're going to decelerate at higher altitude. The higher the altitude, fewer molecules are going to hit you, and so you won't get as high heating. So we kept the same diameter, but we increased the payload weight. We increased by a factor of 2. Actually, ultimately, it was more than a factor of 2. And then we had a lot more energy from the rocket, so we went to a much higher altitude, about twice the altitude. That combination meant we were going to see about an order of magnitude higher heating on this next one.
With the success of IRVI 2, the stage was set for IRVI 3. This would be the most complex mission yet, and would call for the engineering team to make drastic changes to the test article due to the extreme flight regime the craft would experience.
Now, IRVI 3 developed some significant new technology. These aeroshell structure, these toroids, actually making a heat shield, flexible heat shield out of this commercially available materials, proving that it was going to work, making sure all the little pieces are in there was really quite a challenge.
High on the list of important elements for this next test would be to stress the materials in the high heating environment while also testing the ability to maneuver the craft. With the goals set, the team began building the craft.
So this is kind of the forward section of the re-entry vehicle. It has a nose that attaches to the front of this section. We're looking at it, the nose would be down and the tail would be up. This is a section that interfaces with our inflatable aeroshell, and it also houses the inflation system. And the segment above it is the CG offset mechanism, which shifts the center of gravity of the vehicle to allow it to create lift on re-entry. And on top of this would be 2 other segments, a telemetry module and a NIAC segment, an attitude control system.
One of the most interesting aspects of this craft would be in how the team would be able to maneuver it once it came through the atmosphere. Unlike a craft like the space shuttle that has wings and can be steered, IRVI 3 would have to be maneuvered by shifting the center of gravity.
The challenge is, you can kind of think of a surfer. He kind of shifts his weight back and forth on a board and guides himself down the wave. Well, when we're falling in from space, we're hitting the atmosphere very, very quickly. The challenge is we don't have control surfaces like an airplane. The shuttle is a lifting body and we have these body flaps where we can control the direction and trajectory. We don't have the luxury of having a control surface on an inflatable. maybe you could go like the Apollo capsule where it's a blunt body and you can use gas jets to roll, to direct your lifting vector. What we're looking to do is to kind of go back to that surfer analogy where we're actually we want to ride and guide this thing by shifting the mass of the vehicle. So we basically, what we've done for the first time ever, as far as I know, split the mass of an entry vehicle in two. And we're going to drive the back of the vehicle offset from the center line of the vehicle to generate that lifting. You can kind of imagine if we take and we've got a card falling, and as this card is falling, we're going to put a weight on here. It's going to tip it a little bit, and as it falls, it'll slide sideways. So that's the real experiment. Can we actually guide this thing by moving the mass of the vehicle? And it's a challenge because of the loads that run through it. We're looking at 20 G loading on atmospheric interface right at our peak pressure. We're expecting to see 20 Gs. So we're looking at 2 to 4, maybe 6,000 pounds of loading running through this bearing. But the second challenge is, do we understand the aerodynamics of the guidance problem? It's rigid, but it's still flexible, aeroshell, and then we've separated the aft body from the forebody with a joint. Do we really understand the dynamics of that? That's really the question. That's one of the big questions that ERVI-3 is going to be answering.
If you want to steer, then you need to have lift to take you in one direction or the other. We had the ability to rotate it. We just weren't using that capability, but if you were to imagine coming into Mars and we're entering the atmosphere and we know that we're going to, say, go a little long compared to the original planned target, then we could turn it over and have the lift pull us down. Or if we're to the left, we could steer it over and make it pull us to the right. So that's something everybody wants to have. And a Mars Science Laboratory, center of gravity was offset from the center of pressure.
Each piece was carefully assembled, and then it was time to ship it out to NASA Wallops for the flight test. The morning of July 23, 2012 saw the team waiting anxiously in the control room for the flight test to begin. In a matter of moments, they would know if this test would succeed or not.
When the count, is 3, 2, 1, 0, then the rocket ignites and it shoots off of its rail in the right direction. It starts spinning. At this point, we're all along for the ride. The engineers for each of the subsystems monitored what the readings were on their instruments. But for the most part, we were just fascinated by the ascent. It's just kept all of our attention. And one stage burns out in just a few seconds, another stage burns out in 10 seconds. But the main stage, the Brant, burns and ends at approximately 1 minute.
Initial data began streaming in. Everything was looking good. After a few short minutes, the rocket was higher than the level of the International Space Station as ERVI-3 began to deploy.
The next step was to then release the cover that had held our packed aeroshell in place. And it was actually thrown off.
About 709, RV straight cutter.
It took the shape in less than a minute. It was, as far as we could tell, fully inflated, but of course it really was going to take several more minutes before we get to the 20 psi that it needed to withstand the atmospheric entry.
As the data came in, researchers could see that the heat shield was holding its shape perfectly and that the craft was right on course. The next big test would be to see if the center of gravity offset would work. Immediately, perfect numbers began pouring in, proving that this concept had worked beautifully as well. One thing after another was falling into place, with the final crucial measurement on heating to come. The team was hoping to sustain at least 12 watts per square centimeter of heating on the craft, but when the numbers came in, the craft had sustained a heat flux of about 15 watts per square centimeter. This higher number was an even better result, and showed that the material had worked perfectly. By the time the craft splashed down, the team already knew that ERV-3 had far exceeded their expectation and had proven that this concept could work effectively.
All the systems worked. We inflated to the right level, CG offset shifted to where we needed. We had all the cameras with beautiful video of the Earth, and we could clearly see the edge of the perimeter of the back shell, which is what we wanted to be able to see with the cameras. All the instruments seemed to work great. We saw a good heat pulse, went right through it like it was not even there. So everything looked good.
So what is the next step? The team is now working on a concept to develop a larger version of a HIAD called HART, or the High Energy Atmospheric Reentry Test. This mission would release from the International Space Station and would carry down materials that previously would have been released and burned up in the atmosphere. One huge benefit of the HART mission would be that its shape and size would be very similar to what may be expected at a Mars mission.
This concept would be coming back from station, so entering at 7.5 kilometers a second, just like we were talking about at Mars. It would be bringing in anywhere from 3.5 to 5 metric tons, just like we were talking about at Mars. It would be between 8 and 10 meters in diameter, that actual HIAD, just like we were talking about at Mars. And we'll see heating of 25, 30, maybe higher, 35, 40 watts. So it's a very similar environment to Mars for that application. So we can do this flight test from station for a very reasonable cost. And it demonstrates an ability to bring larger volumes and masses down from station than we currently have. And it demonstrates that we could do this mission at Mars.
With a successful HART mission, researchers feel that they may have enough information and knowledge to proceed for the ultimate goal, which would mean seeing a HIAD at Mars.
I believe in the technology, and I think if somebody wanted to give me a budget and say get us to Mars with humans in 2020, I think we could get there. On this technology, I can't speak for other technologies, but no, I think we could get there.
If nothing else, the ERV tests prove what can happen when a lot of smart individuals are given the opportunity to test conventional wisdom and reach for a difficult goal. And because of their efforts, it's conceivable that the idea that began as almost an afterthought may someday be the preferred method of delivering human explorers to Mars and beyond.